welcome to my talk on the anatomy and physiology of Android. Can't claim credit for that title, but hopefully at the end you'll see that that's what you learn a bit about. At the end of the presentation, and this goes really for all the presentations at Google I/O, we ask you to fill out the surveys that they'll be passing through the aisles so that we can get feedback and constantly improve so that we can do an even better presentation next year. All right, so a bit about this presentation. It's a 101 level, but it does assume some basic knowledge of Android. If you've been to some of the earlier talks on Android today, you probably have a good enough background. And it also will cover some of the basics of, to do with Linux. And so, if you have a background in Linux, that will definitely make some of these concepts sink in a bit better. It doesn't focus on how to build an application, and it's not really focused on application developers per se, more focused on what happens underneath the app framework and in the Android platform underneath. And it does not include a device demo. So, wow, you're all still here. That's amazing. Okay. Bit about myself. My name is Patrick Brady. I'm a technology program manager in our Partner Solutions group, and I'm working with Open Handset Alliance members today to deploy Android on handsets. So let's get started. We'll be going over Android anatomy. At a high level, we'll walk through the different layers, the Linux kernel, native libraries, Android runtime, and application framework. And then I'll take you through some Android physiology, starting with a walkthrough of the system at startup and how the different processes kind of evolve from the init process, and walk through some layer interaction, how the applications actually communicate down to the kernel level to deliver the functionality to your apps. Starting with the Android basic anatomy. If any of you have been to any of the talks earlier today or you're familiar with Android at all, you've probably seen this diagram come up many times. This is our basic block architecture diagram. It starts with the Linux kernel. We have the native libraries written in C and C++ sitting on top of those, the Android runtime with the Dalvik virtual machine, the application framework, and the application sitting on top. I'll walk through each of these layers in a bit of detail, calling out some but not all of the components to give you a better idea of how those work. Let's start with the Linux kernel. First, a disclaimer. Android is based on the Linux kernel, or built on the Linux kernel, but Android is not Linux. We don't have a native windowing system. We have no glibc support, and it doesn't include the full set of utilities that you would typically find on a Linux distro, such as Debian or Red Hat or Ubuntu or something like that. But it is based on the standard Linux 2.6.24 kernel. We started out on 2.6.23, and we've migrated to 24 for some added SDIO support, but we'll be holding there for launch and probably hold there until we really have a good reason to go forward. And we have a patch of kernel enhancements, or really Android-specific drivers and utilities that support the rest of the platform. So why the Linux kernel? If we're not building a Linux system, if it's not an entirely Linux system, why use the Linux kernel? Well, number one, it provides great memory and process management. As any OS kernel does, it provides the basic plumbing and services to support the higher level platform and applications. It also provides a great permissions-based security model. This is a security model that's seen 15 years in hostile environments. And we thought Linux was just perfect for that. It also has, a proven driver model, which allows us, to provide a great abstraction layer between the hardware devices, the peripherals such as LCDs, touch screens, audio devices, and the software that's going to use them. It also has support for shared libraries and a real pluggable module architecture that allows us to plug things in very easily. And best of all, it's already open source. It has a thriving open source community that's creating enhancements and moving the kernel along, building in new support for new things such as SDIO or SD card IO, as I mentioned earlier. And it has, a thriving community of engineers who are building drivers to support all of the different peripherals that will power these devices. So going over the set of kernel enhancements we have a basic alarm driver that provides timers that can wake the device up from sleep and based on a monotonic time base. We have our AshMem, or Android Shared Memory Driver, that allows applications to share memory and manages this at a kernel level. We have the Binder, which is an open binder-based IPC driver that facilitates inter-process communication. We'll go over that in a bit more detail. And we have the low memory killer, the power management driver, the kernel debugger, and the logger. We're going to go over two of these in a bit more detail that have gotten a lot of questions and are a bit, I guess, different than your standard Linux facilities. The Binder IPC driver and power management. Okay, Binder. So why do we need Binder? Well, on Android, as you may have learned in some of the earlier sessions today, and if not, you can read about this online or in some of the follow-on talks that you'll see at Google I/O. Applications and services may run in separate processes. So we start all of the applications in separate processes on Android. And yet they must communicate between each other and share data. Typically, IPC, or inter-process communication, can introduce significant process overhead and security holes in an architecture. And so we needed a solution that was really going to be lightweight and powerful enough to be able to facilitate this design of different applications and services running in different processes. So the Binder it's a driver to facilitate IPC. It's high performance because it uses shared memory. So data between applications is not actually copied and marshaled through Java serialization or something like that from one process to the next. It's actually shared through shared memory. The Binder driver manages a per-process thread pool for processing requests, so that services which are registered as Binder services or IPC servers don't need to worry about all the different threads to start up and manage to receive incoming requests. The Binder driver handles that for you. And it has reference counting and mapping of object references so that objects passed between or an application and a service are tracked and can be cleaned up afterwards when neither process is using them anymore. And it supports synchronous calls between processes. And this is important because it means that you stick to your usual programming model, and you don't really have to worry that it's a service running in a separate process. You call it as if it's just a function call or a method call on a class in your own process. Let's see. So let's see Binder in action. Again, you have process A with application A, and you have process B over here with service B. I'm going to introduce one more object here, another object here called context. And this is really going to be an object that's going to provide application A with a reference pointer, a context, in order to locate service B running in this separate process. Think of this as like a single node domain name service or DNS service, where it's going to provide a binding based on a name to the actual service. At runtime, when processes start up, they're all behind the scenes registered with a context object. And so in a typical programming model, the app would just call the context to get a service, which would return the service, and you could call your method, say foo, passing an object over to the service. And that's really what it looks like to the application developer, or to the application developer, or an app calling a service at runtime. But let's introduce the Binder driver, because it's a bit more complicated, and we actually have this service B running in a separate process. And again, the Binder driver spins up multiple threads in each service process, or each binderized process, to handle incoming IPC requests. And this is all transparent to the person building the service. So in this case, when the process A actually calls method foo on the service stub, it's intercepted by Binder, which actually marshals the object and passes a reference of that object over to the receiver, the service here. And so that you're not, again, serializing the object passed in this foo method call, but you're actually passing a proxy to that same object stored in shared memory. and it relays all the method, or relays the method call and the request to these service threads, or these IPC binder threads, which will then locate the actual object, service B, running in that process and make the call. Return the call to the thread, which will then pass it back to binder, which can, take back any objects, again, that are passed back, marshal those back from object references to proxy objects, and pass them back to application A. So it's a synchronous model that allows you to do inter-process communication as if it were running in your local process. The nice thing about this as well is because of the way it doesn't serialize and deserialize objects, there's no incremental overhead for calling services that are actually running within your own process. And so in cases where you do have services running in the same process, and we'll get to some of those later, you don't incur any of the overhead with IPC. But the nice thing about Binder, if you're an application developer, is that you don't really need to know all the low-level plumbing. If you look at the AIDL, or Android Interface Definition Language, and there's information on that on code.google.com in the reference documentation, you can look up how to create services where all of this plumbing is handled for you. Okay, moving on to power management, or PM. There's two facts about mobile devices that are going to hold true for the foreseeable future. Number one, mobile devices are going to run on battery power. I don't think the solar and nuclear-powered devices are really going to be a hit anytime soon. And batteries have limited capacity. I'm sure many of you out there in the crowd today brought your chargers because your batteries have maybe more limited capacity than you would like. So Android took a more aggressive approach to power management. It does not replace Linux power management. To be very clear, a lot of people in the Linux community have asked us, why are you building your own power management solution? We have power management built into Linux and the kernel. Well, this is not a replacement for power management. It's built on top of power management, and it's really a more aggressive policy that believes that if no application or service specifically requests that the CPU or the LCD be kept on, we're going to shut it down so that your mobile device will last longer. And components can make, applications and services can make requests to keep the power on through the concept of wake locks. We have partial wake locks, which say, keep the CPU on, but I don't really care about the display. Maybe I'm playing an MP3 in my MP3 application, and I don't really care if the display times out because I want to save power, but I don't want the CPU to shut down because I want the music to keep playing. Or you may request a full wake lock. And a full wake lock would say, maybe I've created an application which is displaying my position on a map, and I want the display to stay on at full brightness while my location is moving around so I can see where I'm going. And there's other types of wake locks that we won't walk through here, but they're all basic variations on these. So if we look at power management in action, excuse me, you have application A again. You have power manager, which is really just a higher level abstraction on the power management driver. And you have the PM driver here. So application A is going to request a wake lock saying, I need a partial wake lock. Again, maybe it's playing an MP3, something like that. And the power manager is going to pass down through the stack, and this is obviously a simplified drawing here, and return a wake lock. So at that point, the CPU is kept alive, and it's not going to shut down. Now you're playing your MP3. Maybe because this is just a partial wake lock, after, say 10, 30 seconds, whatever the user's configured, it's going to turn off the LCD if you're not doing something else with the device. Then when you release the wake lock later, maybe the user stops playing the MP3, you give up the wake lock, we're going to immediately, the power manager will pass down to the driver to destroy or release the wake lock, and we're going to immediately turn off the CPU if there's no other processes asking it to stay alive. Just for those of you who aren't familiar with mobile processor architectures, that doesn't mean that we're going to shut the phone off and you won't get any calls. That's just turning off the application processor, and so there's still a modem processor there that will receive calls and be able to wake up. But anyway, so this is, again, just a much more aggressive policy on power management, where if you don't specifically ask for the CPU to stay alive, we are going to shut it down. And this is required because we're taking Linux from a traditionally desktop environment where you have it plugged into the wall and you have virtually unlimited power to a mobile environment where you have fairly limited battery life. But again, as with Binder, most applications don't need to really worry about the low-level details. They need to, basically understand the concept of wake locks and use them carefully. You don't want to keep a wake lock on indefinitely because it's going to keep the CPU going, especially a full wake lock, keep the LCD alive, and that will make for a very bad user experience. And you have the alternative option of using user activity and specifying when the last user activity was, so that if you're doing something like what Steve showed in the keynote today, where the user may not be touching the screen to generate input events, they may not be touching any keys, and yet when you're moving around and using the accelerometer, the application wants to keep the device alive. And so something like that, you could use user activity and pass in a time, and that will keep the display alive and keep the CPU alive for some amount of time. But underneath, it's using the same concept of a wake lock. There's more information on the Power Manager online on code.google.com, and for any more information, check it out. Okay, so the entire kernel source, again, is available today at git.android.com. For any of you who aren't familiar with Git, or sometimes pronounced JIT, it is the source configuration management solution that kernel.org uses for the Linux kernel. I believe it's some slang meaning an idiot in some British slang. But anyway, that's what Linus Torvald decided to choose, and that's what we're following on. Following our commitment to open source all of Android, we're getting started early with the Linux kernel, and we've open sourced that all. We're posting patches on pretty much a weekly basis up to git.android.com, and so you can check that out there. Okay, so moving on. Sitting on top of the Linux kernel are the native libraries. Again, written in C or C++. These are the libraries that provide low-level functionality and computation-intensive services to the Android platform. I'll walk through a couple of them here in detail to give you a better idea of what's really powering the platform. And I'm going to break these down into four major groups here. Bionic libc, function libraries, native servers, and the hardware abstraction libraries. This is somewhat of an arbitrary grouping, but it's my talk, so let's see. So starting with Bionic C, any discussion of the native libraries really has to start with Bionic C. This is our custom libc, or C runtime implementation. It's different than what you would find on a standard Linux distribution, again, like Red Hat or Ubuntu or something like that. And just like Power Management, just like Binder, it's optimized for embedded use. We're always building the platform with the underlying belief that this is going to run on mobile devices, and we need to design for that. But why Bionic? There's a lot of overhead involved in maintaining your own C library, and we've gotten a lot of questions from the Linux community about that. Well, number one, we wanted to address the licensing problem with the standard C library. So the standard C library is GPL, or the General Public Use License, which has a nasty copyleft clause, which means that anything that is built with GPL code needs to be open sourced itself. We have a lot of people who want to write proprietary code, that contains intellectual property and keep that as closed source. Secondly, size, because libc, as we'll see later, is loaded into every process that has some native component, which is basically every process. It needs to be small. This isn't running on a desktop computer with gigabytes of RAM, so this needs to be small. And lastly, it needs to be fast. CPU power is at a premium, and so we need to be very fast. So Bionic, we're distributing this under the BSD license, or the Berkeley Software Distribution License. The code comes from a mix of the different BSDs, NetBSD, OpenBSD, FreeBSD. These are different C library implementations based on the BSD license, which is free of the copyleft clause. And so it allows people to keep things as closed source. It has a very small size. It's about 200K, which is about half the size of your standard glibc library. And that makes a big impact if you're loading this into multiple processes running on a device. And it also has fast code paths. We have a very fast and custom pthread implementation, which uses 4-byte mutexes instead of the standard, I believe, 12-byte mutexes. And so it makes threading and everything like that very fast. We're running on a mobile device. We're not going to be spawning off, millions and millions of threads like you may be on a Linux server. And so we've scaled this down to make it very tight and fast. It also has some built-in support for some Android-specific services. A quick way to get default system properties, as well as log capabilities to be able to log a message with priority info or debug and things like that. So what some people who are big proponents of glibc may consider bad news is it doesn't contain certain POSIX features. We don't support C++ exceptions because these are just too heavy for embedded devices. We also don't support wide characters because we believe that those are better handled by International Components for Unicode or ICU libraries. It's not compatible with GNU libc. We do implement some of the GNU libc extensions, but not all of them. And this means that all native code, and again, today through the SDK, we're not really exposing developers with the ability to build native components. But when we do open source the platform, all native code will need to be compiled against Bionic or libc if it's going to be compatible with Android. The added benefit is if you build something with libc, you get all that high performance and that compact size. Okay, so moving on to the functional libraries. And again, this is my naming for them. It's not an official name, really. But these are the libraries that are providing a lot of the power behind the Android platform. They're abstracted by the higher level APIs that you'll see in the application framework. But this is really where the heavy lifting is done. And we'll walk through a couple of them here. The WebKit browser, you heard Vic mention that in the keynote this morning, and I'm sure it's been mentioned in some of the other talks, but we really believe that this is the best browser engine out there. It's the same browser that's used in Apple's Safari. It's used in some of the newer Nokia Series 60 devices out there, and we really believe it's the best browser engine. It supports full desktop rendering, full CSS, JavaScript, DOM, AJAX support, so it allows you to build rich web applications. And we've added some support for single column and adaptive view rendering to, again, tweak it for embedded devices. But this is based on the same open source WebKit browser that you have out there today. Really powerful. The media framework. Media framework, it's based on Packet Video's open core platform. This is the open source initiative for their core platform. I saw some Packet Video people in the crowd earlier. I'm not sure if they're still here. But it's a really powerful platform that gives you all of your standard codecs and file formats. So MPEG-4, H.263, H.264, MPEG-3, AAC. All of these will be provided as software codecs and open sourced with the platform under the Apache 2 license. But I heard a question in one of the earlier talks. Well, what if some of the codecs aren't supported that you need in your application? Or what if you want to provide a hardware accelerated codec? Well, we support codec plugins, either hardware or software, via the standard OpenMax IL interface, which is an interface defined by the Kronos group. It's a standard interface for exposing hardware codecs. And so if you have a high-powered chip on a very a more expensive phone that supports a hardware MP3 decode, that's going to save you power. It's going to provide better performance and maybe better quality. And so that we support plugging those in at runtime. SQLite. So one of the things we knew we needed when we were building Android was a high-powered transactional data store, a relational data store that would give you really the power of building desktop and web apps on a mobile device instead of just reading and writing from flash memory. And so we've chosen, again, another great open source project out there, SQLite. It's available under the public domain license. And we've integrated this into the platform. This really provides the back-end storage for a lot of the persistent data on the Android platform. Your contacts, your MMS, your SMSs. All of these will be stored behind a content provider, if you're familiar with those, in a SQLite database. And now, moving on, we'll talk about native servers. These are processes which are running and really doing some of the heavy lifting to control the input and output devices on the platform, running on a device. The first one we'll talk about is Surface Flinger. This is a very powerful server, which is really the system-wide composer for Android. So it takes surfaces drawn by different applications running in different processes and composes them all onto the single frame buffer to output to the device display. It can combine 2D and 3D surfaces onto a single output source, and it really makes it easier for all of these different applications not to worry about what they're writing to or how they're being rendered. You just send it down to the Surface Flinger, and it will composite them together and get them out on the frame buffer. So surfaces are passed as buffers via binder IPC calls. So again, that's it's a very high performant way of passing these from different applications and out to the Surface Flinger and down to the frame buffer. We can use OpenGL ES and 2D hardware accelerator for its compositions. And just like we have on the media framework, you can plug in hardware acceleration if you have a 3D chip on the device through the OpenGL ES or EGL interface, again defined by the Kronos group. If you go to kronos.org, I believe, it will provide information there. And it does double buffering through. It basically paints to the Y plane on the frame buffer. So if you have a device that is maybe HVGA, it will allocate twice that for the frame buffer and paint one buffer while it's painting there to the background frame, and then pan the device pan the frame buffer when that's ready, so that you never have buffers written to screen that are partially drawn while the user is viewing them. Moving on, Audio Flinger. Audio Flinger really is what Surface Flinger is to the display devices. Audio Flinger is to audio devices. And so it takes audio output streams from different applications running in different processes that are outputting simple tone audio or maybe game audio, a race car sound that's being generated by a game, or media player audio, such as an MP3. And it routes all of these to the various output devices, whether that's an earpiece on the device, a speaker phone, or a Bluetooth headset. And it can sit on top of many of the standard audio implementations or drivers on Linux, such as ALSA, the Advanced Linux Sound Architecture, or OSS. So again, this isn't replacing any of the standard Linux audio implementations. This sits on top of those and provides the Android-specific features to the platform. And actually, that's a good segue to the hardware abstraction libraries. So how do we sit all of this on top of these different Linux implementations? Many of the OEMs now have, handset manufacturers now have Linux distributions maybe on their mobile platforms. And they have the drivers to control their displays. And they have the drivers to control audio and their touchpads and things like that. And so we have a set of hardware abstraction libraries that really provide a better abstraction layer between the hardware and the upper layers of the Android platform. To give you just an idea of where these would sit, I'm kind of changing the overall architecture diagram a little bit to show you that these are native libraries sitting down there in the libraries layer. And they contain abstractions for things like audio and camera or Bluetooth, GPS, the RIL or radio interface layer to talk to the modem baseband, Wi-Fi, and many more. Again, it's a user space, C and C++ library. It defines the interface that Android requires of the hardware. So, ALSA for audio may implement or may expose a huge interface with all sorts of different things that you can do with audio. And our audio hardware abstraction layer definition is just going to define what Android needs of audio. So you can plug in ALSA or OSS or anything else below. And the goal here is to make porting easier. We're trying to define a clear set of APIs in the same way that we have for application developers through the SDK. We want to define those for anyone that will be porting Android once it's open source onto real hardware so that they don't have to dig through the 10 million lines of source code to figure out how to get this working. They just implement drivers for these specific interfaces. Now, any Linux gurus out there or people who are paying attention when I said earlier that the Linux kernel provides a great abstraction layer are probably asking, well, why do we have another abstraction layer on top of the kernel? Well, the real reason is, and we debated this internally for a while, not all components have a standardized interface in the kernel today. So you have things like, a vibrator driver for your device or an LED driver. These aren't always exposed as standard kernel drivers. And the other problem is kernel drivers are GPL, which exposes the intellectual property. Like I said, that copy left means that if you, put anything in the Linux kernel, it pretty much needs to be shared as open source software. And we found that as much as we want to ship everything as open source, there's a lot of handset manufacturers and chipset providers out there who feel they have a great deal of intellectual property in their drivers, and so they want to keep those closed source. So we needed to provide a way to do that in user space outside of the Linux kernel. And lastly, like I said, Android has specific requirements of the hardware, and we wanted to make sure that those were well documented and defined in interfaces so that people could implement those without having to figure out, which driver interface in the Linux kernel to use. So a simple example of what we're doing in our hardware abstraction library headers, we just have a header that would define the functions that Android would require. I'm using a very dumbed down example here, but for if I had some Acme component that I wanted to plug in, okay, say this is audio, we would have a struct that defines your different function pointers, and you would have an init function that allows that Android can call to get a reference to those functions. Anyone implementing a hardware abstraction library or a hardware driver in user space for, say, audio would compile a shared library or link this into a shared library that would be loaded on the device at runtime. So at runtime, we would just call from Android the DL open and load libacme and bind that to the functions that we need in the Acme component. If this was audio, we would do something libaudio, and then get a pointer to the audio functions that we require. And this allows us to do very loose coupling between the lower level hardware implementation and the rest of the Android platform. Okay, so we've covered the native libraries. We've covered everything down to the Linux kernel, and the real magic of the Android platform happens in the layers above this, and that's what we'll go into now, starting with the Android runtime. So the Android runtime sits on top of the libraries in the Linux kernel, and it provides, number one, the Dalvik virtual machine and the core libraries here, written in blue because they are exposed through the Java programming languages. Excuse me. So the Dalvik virtual machine. Remember, Android is not Linux. We don't have a native windowing system. All of the applications and services that you run will be running inside of a virtual environment powered by the Dalvik virtual machine. This is very important because it provides application portability, meaning that an application written in the SDK will run on different devices that maybe have different low-level hardware implementations, are compiled with different tool chains and things like that. They will all run on the same virtual environment. And it does not. One important thing to call out: it does not run Java bytecode. So Dalvik runs an optimized bytecode called DEX, or Dalvik executable, and this is very tuned again for the embedded environment. The bytecode, the Dalvik virtual machine, it's lightweight like libc, and so it supports running the virtual machine in multiple different processes on the same device. We needed to make this very lightweight. There's a great talk, Dalvik VM internals, that our lead Dalvik engineer, Dan Bornstein, will be giving at Google I/O, and I encourage you to check that out to learn more about it. But it's highly CPU-optimized bytecode interpreter, and it uses runtime memory very efficiently. Data structures are optimized to be passed between processes. It uses fixed width data structures so that parsing time is much faster. So it's really just optimized for embedded use. And sitting on top of that are the core libraries. Underneath, you have this extremely powerful VM, and you have all of these libraries exposing OpenGL for 2D and 3D. You have the powerful audio Flinger and things like that. But we wanted to expose to application developers a very simple set of APIs that they were familiar with. And so the core libraries provide you with the standard data structures, utilities, file access, network access graphics that you're used to in the standard Java programming language. Okay. Now moving on to the application framework. Again, the application framework sits on top of the Android runtime. It's written in blue, again, signifying that this is all written in the Java programming language. And it contains all the classes and core system services that will be used to build applications, whether those are the core apps that are built by the Open Handset Alliance and will be open source today, or will be open source in the future, such as the Home app and the Dialer app, or whether it's apps like Pac-Man that you saw earlier today in Steve's demo. They all have access to this same set of application framework APIs. It provides Java language bindings for the native libraries, and so we have an abstraction for OpenGLES and things like that that run in the application framework. Let's see. So moving on to the core platform services. These are really part of the application framework, and these provide the services that are essential to the Android platform, that manage application lifecycle, that manage packages and loading and resources and things like that. And they're working behind the scenes. You typically don't interact with them directly when building an application, but they're running behind the scenes, and they really make the entire Android platform tick. So starting with those, we have the Activity Manager. It manages the application lifecycle for all activities, tells them when to start up, when to shut down, or not shut down, but basically be persisted to memory so we can reclaim space. It maintains a backstack so that you can navigate through applications in the same way you do on the browser, going from one application to the next, going from an email, clicking on a link, going into the browser, clicking on an address in the browser and going to the Maps application, and then click back, just like you do in your browser, to have seamless navigation right back to the email you started in. Let's see. Moving on to the Package Manager. This is used by the Activity Manager to load information about all of the APK files, or Android package files, on the device. And these are just archives that include activities and intent receivers and things like that, or services. And the Package Manager will tell the rest of the system what applications are loaded on the device, or what packages, and what the capabilities of those packages are. And we have the Window Manager. This sits on top of Surface Flinger and basically handles all of the various windows drawn by different applications, manages the Z order of those so that you know which ones should be showing in front of the others. And again, sits on top of the Surface Flinger, passes everything down to the Surface Flinger to render on the device. The Resource Manager handles all non-code resources in an application or service. So these are things like externalized text strings, or an image file that you may include, or audio files, things like that. Content providers, these are components that allow you to share data between applications. And so, we have a content provider that provides access to the contacts database on the device. And you can share that between different applications so they can all have access to that data. Again, many of these are backed by a SQLite database, but it may be backed by something else, a network storage or flat file access. We have the view system, which provides all of these standard widgets like buttons and a date picker view and the map view and things like that to build applications. A rich set of widgets there, and also handles all of the layouts so that you can have a button inside of a table, inside of a frame layout on an application. So it manages the view hierarchy and makes sure that each of these components is rendered in the appropriate space. Okay. But we also have a whole list of hardware services, things that aren't maybe intrinsic to the Android platform, but provide you access to all of the lower-level hardware features on the device. So we have, they're typically accessed through a local manager object through, again, the context, as we saw before. So you would just grab, like location manager here, grab it as a system service from context, and cast it. And so then you have a handle to the local stub. So you have things like the telephony service, which handles all communication with the baseband radio through the radio interface layer. You have the location service, which handles all access to the GPS device. Bluetooth service, Wi-Fi service, USB service. All of these services will be accessible to application developers so that they can build rich applications which make full use of the device, including a sensor service that can handle some of the things like Steve showed this morning with a compass or an accelerometer to allow you to do really cool things that you don't see on mobile devices very often. Okay, so the application framework, there's a lot to cover, and we're not going to go over everything. We'll just concentrate on those few components. There's more information at Google I/O if you want to check out Dan Morrell's talk on Inside the Application Framework, and online at code.google.com, Android. Okay. Yeah. Should have turned that off. Okay. Let's see. So we've covered, the Linux kernel, the native libraries, the Android runtime, the application framework. The last piece to go over there is the applications, but we're not going to spend a lot of time on that today because we have some other things to go over. But basically, the applications sit, like I said, on top of the application framework, and they have access to all of these core system services, hardware services, and the core application framework to build great applications. So the thing to stress here is that the applications we're building for the Android platform, including the home, the dialer, the SMS app, the email app, those are all using the same services and the same SDK that's available to application developers to build other services or other applications. Okay, a quick walkthrough of Android Physiology. We'll start with the startup walkthrough and look at what the system looks like and how it builds up from a single process out to the multi-process environment we have in Android. Like any Linux-based or Unix-based system, at startup, the bootloader is going to boot Linux, and it's going to kick off the init process. This is similar to how any Linux system really starts up. The first thing init is going to do on Android is start some low-level processes called Linux daemons. And these are typically used to handle things like low-level hardware interfaces. They would sit on top of the hardware abstraction layer and run and listen on sockets for things like USB connections or an Android debug bridge or ADB connection, the debugger connections, and also the radio interface layer daemon, which will sit on top of the radio baseband and interface with the baseband modem. After starting up the Linux daemons, and we'll collapse those in the corner of the screen here to save some space, the init process starts up a really neat process called Zygote. And as its name implies, Zygote is really just the beginning of all of the rest of the Android platform. And so Zygote is a nascent VM process. It initializes a Dalvik VM and preloads a lot of these libraries. And it forks on request to create new VM instances for managed processes. Again, every application is going to run in its own process, and we don't want to do a cold start on the VM to start those up. It uses copy on write to maximize reuse and minimize footprint, so that data structures are shared, and it won't do a full copy unless some of those data structures have been modified and it needs to. So the next thing that init does is it starts up the runtime process. And the runtime process does one very important thing. It starts the service manager. And this is really the context object that we had talked about earlier. It provides the really DNS or local lookup service for all of the services controlled through Binder. And it registers that service manager as the default context for Binder services. Then the runtime says, okay, I'm ready to really start managing processes. Let's go. And it sends a request over to Zygote asking it to start up the system server process. So Zygote splits and starts up a new Dalvik VM with the system server. This is the first managed process that's started up, and it's really brought us, up into the blue layer on the Android stack diagram. The first thing system server does is it starts up Surface Flinger and Audio Flinger to be able to control the display device and the audio output devices like we saw. And that's where you'll see, the spinning or the back and forth red dot on the Android emulator. These are going to register with the service manager so that they're available for other applications and higher level services to call on them. And again, we'll collapse those. And the next thing that the system server is going to do is start up all of those core platform services and hardware services that we talked about earlier. So the content manager, the telephony service, the activity manager, the window manager. And it's starting all of those up within this same process. In the same way, these are going to register. And they actually register through a Java proxy object, which is basically a pass down to the service manager here. So it's a Java representation. And they register and say, okay, I'm the activity manager, and I'm ready to accept calls. I'm the package manager, and I'm ready to accept calls from other processes. So at this point, you have more or less the full stack ready that needs to be there for the first activity to start up. This is where we sit in terms of processes. We have the init process. We have these multiple daemon processes running, the runtime process, our original Zygote, which will stick around and continue to listen on a socket for any more requests to fork off and create new VMs. And we have the system server process, which has all of our core services and platform components. And at this point, we're ready to launch the home application, or the idle screen, as many of you may know it. And so Activity Manager will actually send a request to Zygote and say, all right, I want to start an activity that subscribes to the main intent or the home intent. And that will cause Zygote to fork off and load this new process with the home activity and a new Dalvik VM. An important thing to note here, and I can see I'm actually missing one on my diagram, but libc is running in every process. And we now have 3 Dalvik VMs running in every process. And so this just goes back to reinforce what I was talking about earlier. It's very important that everything in the Android architecture was designed to be very compact and efficient so that it can run in a multi-process environment. So when the user maybe loads home and then hits the Contacts app, that will again start off a new Dalvik VM, new Contacts app, and load a new version or a new instance of libc running in that process. Okay, so we've shown how that builds up at runtime. Let's take a look at how the layer interaction works down through the applications, down to the kernel. There are 3 main flavors of Android layer cake that we'll go over today. Slight variations on this, but we'll concentrate on these. Starting with an application talking to a runtime or a managed service, and down to a native library. So an application would make a binder IPC call, again, through the context object behind the scenes, to a runtime service running in the application framework. We typically have, on a lot of these runtime services, we'll have a native service binding, or a native component to that service, which is connected through the Java native interface, or JNI. And this gives the native service binding a way to access these hardware abstraction libraries that we talked about earlier, so that it can do a dynamic load and load, libc so, which can then talk to the Linux kernel. And a good example of this in our Android architecture is a location manager service, where if it's not using a software implementation or a network-based location, and it's using an actual physical GPS chip on the device, it has the GPS location provider, which is, has two halves, the managed half and the native half, communicating through JNI. Does a dynamic load on the libgps, which then communicates to the kernel driver to talk to the GPS chip. So the second variation of layer cake that we have in Android is the app calling a runtime service, calling a native service, and then calling a library. So we have the same basic structure that we started with earlier, except now we're doing another binder IPC call to a native service, which will do a dynamic load and talk to the kernel driver. A great example of this is the media player. You have a media player in the Android framework, which you can load to play, stream resources off of the internet or play local media files. It's connecting down through JNI to a native implementation of the media player, which will talk to the Packet Video Open Core framework. But it will also make a call out to Audio Flinger over inter-process communication in the binder, which will actually load libaudio and talk down to the Linux kernel. But again, libaudio is really where we draw the line of what the Android platform is. And so other architectures can implement ALSA if the particular Linux distribution running on the device has an ALSA driver to expose the audio. Or it could call a proprietary audio driver. Maybe someone has a lot of IP tied up in their audio. They have voice cancellation and other things that they don't want to expose. Android will sit right on top of that. And as long as it's exposed through the same interface as we talked about earlier, we'll be able to call that all the same. And the last one, which I'll try to go over quickly so we have some time for questions, is an application talking to a runtime service, and again, talking to the native daemons. Remember those daemons that we started up when we were, the init process started up when we were initializing the system. So again, the same basic architecture from the application perspective. It doesn't really need to know anything that's going on underneath. And here, we're talking over sockets to a Linux daemon. Now, why would we choose a daemon here instead of a server? Well, this is typically used in cases where you have a very simple protocol and you're not passing objects back and forth that need to be tracked for references and things like that. You're just talking over a socket using a simple API. And the daemon here in this case will launch the HAL library and talk to the kernel driver. A great example of this is our telephony stack. So the telephony stack talks down the telephony manager, which is actually a collection of APIs, which we've kind of grouped here. But talking over a socket at the native layer to the RIL daemon, or the radio interface layer daemon, which will talk to the baseband. And so Android today can run on a Marvell chip or a Qualcomm chip or a Broadcom chip. And we don't really care what the underlying modem connection is. We just talk to the RIL daemon and load libril.so. And so anyone building a new interface to a new radio can just drop that right in. Okay, so that covers it for the flavors of Android layer cake. We've walked through all of the components in the Android architecture, and we've talked about how those interact at runtime. And so that's pretty much it. We can open it up for Q&A. We have about 6 minutes left. There's microphones, one on this side and one in the middle for anyone that wants to ask questions.
I have a question for you on the media libraries. When we're running the emulator, are we running the real packet video media libraries, or are we running something that kind of shortcuts through to Windows or Mac?
Oh, that's a good question. I believe you're running the real packet video media libraries. Android, the real thing to point out there is that we've packaged an emulator that emulates an actual ARM architecture processing environment and emulates what will be running on an actual device, rather than a simulator which would just make it look and feel like it's Android, but actually run something different underneath. And so the emulator will run the same code that you see on a device. And you should have roughly the same performance. And in some cases, we've seen better performance running on actual hardware.
So if we notice a problem with that, like I wrote a program, you press a button, it plays a note, and there's a delay. Does that indicate a real problem with the packet video codecs or whatever, or does it indicate a emulation problem? It's probably related to that. The main thing here to remember is that we've published an early access look at the SDK, and so a lot of this stuff, for example, that Steve was showing during the keynote speech today, is far advanced beyond the previous SDK which we've launched. So I think a lot of those issues have been worked out, and you'll see those in the next SDK release. Okay.
Hi. I think I have kind of the same question, but it's a little bit different. When we check the code for the telephony manager, in the M3 version, for example, it's like some stub functions, and in 5 there's like some more data, but it's not real implementation. So when you mentioned the libreal.so file there, the source code for that, or at least the mockup driver for that, will be part of the 2.624, the latest kernel release that is on the git.google.com?
Yeah, so that's a good question. So remember that Android, we really, those shared libraries that we load at the native layer, those could be any number of different things. And so you may have a RIL that's based on a Qualcomm modem. You may have a RIL that's based on a Marvell modem or something else. And what Android will provide when we open source, we'll provide a reference implementation that will basically give the basic feature set, but may not be commercially ready at that layer. And so other people for commercial distributions will actually plug their specific drivers in. Yes. So the reference RIL, it actually sits in user space, and right. So we haven't open sourced that yet today.
Okay. The second question would be what will be the difference if you use insmod as opposed to DLOpen like you had in your example there? It should be the same, right?
To be honest, I don't know the details of that.
Because we tried it and it seems to work. But when I saw the DLOpen, I was like, wow, maybe we did it wrong.
Our engineers are looking at that. And this, what we've published here as part of this talk, you may find things change before we actually open source the code.
All right.
But that's a very good question. Last question.
You had indicated that the Dalvik VM was written optimized for the CPU. Can you give us any insight into which CPU architectures it will be?
Currently, it's optimized for an ARM architecture. I don't know which specific ARM architecture we rely on for Dalvik specifically. Again, as I said, Dan Bornstein's giving a talk, and so he'd be best to answer that. But we do have people looking at ports to other architectures. Okay, and that's it. I'll be around up front if anyone has some follow-up questions. Do you need to